Okay, everyone. Hello. I hope you had a great March break. Let's get started. 6.3. So I would encourage you to try these examples before watching the solution and then kind of coming back when you get stuck, but it's here for your reference. Beginning with this first problem, our goal in this is to verify that this equation is true. And we know the difference between verifying and proving, of course. We talked about it quite a bit, but verifying is just to suggest that, okay, this might be true, and we can verify in two ways, either graphically or by substituting a value for x. But before we start doing any of that, we of course have to state our non-permissible values. So let's go to this very first example. So considering over here that we have tan x in my numerator, I know that tan x must exist. So that's going to eliminate some x values. Mainly, it's going to eliminate, that means x cannot be pi over 2 and 3 pi over 2, because those are the values where x is not going to exist. And of course we want that in general formula, so that means that x cannot be pi over 2 plus or minus pi n, where n is an element of whole numbers. Okay, so that's 1. Now what about cosecant? Cosecant, of course, has its own restrictions. So cosecant, of course, then cannot be equal to 0, since it's in the denominator, which eliminates, what are some values? So that eliminates, actually, it eliminates absolutely nothing, since cosecant will never be equal to 0. And if you're not sure about that, let's just think back to the graph we sketched. We can see that there's kind of a rough sketch of what cosecant looks like, and it's never equal to 0. It's always going to be greater than 1 or less than negative 1. So we don't really need to consider it anymore. There we go. All right, let's continue on now with our graphical and our substitution method of verification. Now graphically, I'm going to let you work on this on your calculator. So for y1, you're going to want to use tan and x cos x over cosecant x. Keep in mind that for cosecant, you're going to probably have to use 1 over sine x. And for y2, you want to take a look at the left side, the right side, which is 1 minus cos squared x. And I would encourage you again, if you scroll all the way to the left, to change one of the functions, usually the second one, to have that loop. Since then you'll be able to kind of see that it has has overlapped with the other function. All right, so let's work on this proof over here, not proof, but our verification that requires a substitution of a value of x. So what are some values of x that are good? You haven't highlighted a value here to use, so you can really use what you want. What I would encourage, though, is, well, I guess, first of all, not to use an MPV value, and also really not to use pi or 0 or pi or 2 pi or pi over 2s and 3 pi over 2s, because you run the risk of getting a value of 0, which isn't really going to do a very good job verifying anything. So I like to use something like pi over 4. And I can use an x value of pi over 4. I know that tan of pi over 4 is 1, and I know that I kind of get these values that I can work with. So that's my plan. So let's start with this one, and let's start with the left side. We're going to take a look at tan of pi over 4 times cosine of pi over 4 over cosecant of pi over 4. All right, well, first off, let's zoom in here a bit. And we know that tan of pi over 4 is 1. We know that cos of pi over 4 is 1 over root 2. And we know that cosecant of pi over 4 is root 2. And that simplifies to be, okay, 1 over root 2 times 1 over root 2 times 1 over root 2, which becomes 1 over 2. Okay, let's take a look at the right side. The right side being, scroll over here, 1 minus cos squared x. So of course we're using the same x value, so that's 1 minus cos squared of pi over 4, which is 1 minus 1 over root 2 squared. Oh, that's 1 minus a half, which is a half. Great. So verification complete, my left side is equal to my right side. Now this of course doesn't prove anything. I have to prove algebraically, but what it does do is suggest that a proof is worth my time. So let's try proving this. Proving it means that we need to algebraically change one side to look like the other, or change both of them so that they look like the other. So let's start over here. Let's start with our left side, because to me it looks the most complicated. So I have 10x cos x over cosecant x. So let's do some manipulating here. Bring this down a bit, give myself a bit more room, maybe even zoom in here. Okay, so starting over here, well, what are some things I know I can change immediately? I know I can change 10x to sine x over cos x, and then cos x will stay where it is, and cosecant I can also change to 1 over sine x. So what does this leave me with? Well, I know this cos and this cos will cancel, which is great. So really I'm left with sine x over 1 over sine x, which is equal to sine x times sine x over 1, which is sine squared x. Now this is really, really close to what I have, but but not quite, right? I actually need 1 minus cos squared x. Well, is there an identity that can help me here? Yes, there is. I know that the Pythagorean identity says that sine squared x plus cos squared x is equal to 1. Well, that means sine squared x is equal to 1 minus cos squared x. So here I can substitute, instead of sine squared x, 1 minus cos squared x. There you go. Therefore, left side is equal to my right side. Excellent. Right. Well, that was just the beginning here. And to take a look at some of the other proofs we're going to look at, I just wanted to give you a summary of some helpful ideas here. So first of all, simplify both sides to identical expressions. So sometimes you're going to see that both sides are pretty complicated, and you might have to manipulate both sides to get them to look the same. I tend to start with the more complicated expression, which I think is quite intuitive. You have to be able to do something. And some strategy you can use. You can use known identities to make substitutions. If quadratics are present, consider the Pythagorean identity like we did above, and rewrite using sine and cosine, usually. Now every expression is a bit different, but these are some tips. And factor to simplify expressions. Another one to consider is multiplying by the conjugate. So if I see that an expression, and this is just a very short example, if I see the expression looks like this, 1 sine x is equal to 1 plus sine x, for example, over something, I can see that this expression and this expression are conjugates. So sometimes it's nice to multiply one side by the conjugate to get there. Okay, so we're going to continue looking at a couple examples, and hopefully it'll help prepare you to work on that assignment. Okay, let's take a look at the second example, starting with the non-permissible values. So I know that cos 2x plus 1 cannot be equal to 0 because it's in the denominator. So that means cos 2x cannot be equal to negative 1. Now this happens when 2x is equal to pi. So cannot be equal to pi, and then of course plus or minus 2 pi n, since we're looking at a general solution. And I can divide both sides by 2 to actually get what x cannot be, which is pi over 2 plus or minus pi n, where n is an element of whole numbers. So we've taken care of one non-permissible value here. However, when we think about tan, well, tan x actually has the exact same non-permissible value. So I'm pretty much done. So there we go. So let's start proving this identity. Now I'm going to start with the left side. Hopefully that kind of makes sense. This is the most complicated side. So let's take a look at what we have. So on the left side, we have that sine 2x over cos 2x plus 1. Okay, well, what are some things I can change? Well, I can see that I have double angles. So that's where I'm going to start. I'm going to start with double angle identities. So that means that instead of sine 2x, I'm going to write 2 sine x cos x. And in my denominator, I have cos squared x minus sine squared x plus 1. All right, well that's pretty good, but not quite where I want to be. I need to get to tan x. Now tan x is sine x over cos x. Now that suggests to me that in my denominator here, I need to have a cosine, and in my numerator, I need to have a sine. And when I see cos squared or sine squared, I automatically think about Pythagorean identity. So let's use that. So Pythagorean identity, just like we used on the last example, I think I'm going to substitute sine squared because I know I want cos in my denominator. So I know that sine squared x is equal to 1 minus cos squared x. So let's use that. So that means 2 sine x cos x over cos squared x minus 1 minus cos squared x plus 1. Simplify this a bit more, and I get 2 sine x cos x in my numerator, and in my denominator I have 2 cos squared x, and that's it. The 1, I have minus 1, then I have plus 1, so it's going to cancel out. If I look at what I have now, well, I can simplify the 2, I can simplify one of those coses, and I'm left with sine x over cos x, which is tan x. Awesome. So that means my left side is equal to my right side, and I've proven this identity for all values of x except our non-permissible values. Let's take a look at the next example. So looking over here, I see that I have a slightly more complicated expression, but let's start with our non-permissible values. So we know that cos x can't be equal to 0, which means that x can't be pi over 2 plus or minus pi n, where n is an element of whole numbers. So that means it can't be pi over 2, can't be 3 pi over 2, and so on. Also, sine x cannot be equal to negative 1, which is going to eliminate only 3 pi over 2. So x cannot be 3 pi over 2. Well, plus or minus, 2 pi n. Let's finish that off. Well, this NPV is included in the first one. So really, this is my only non-permissible value, since it includes both. So let's go back to simplifying. Now in this case, I think the right side is going to be the more complicated side, so I'm going to start there. I have secant x minus sine x secant x over cos x. Oh, you know what? I think I actually forgot. Did I? No? Let's think about this. Well, secant has to exist, but secant doesn't exist when cosine is equal to 0. So that means by identifying where cosine is equal to 0, we've already taken care of the NPVs for secant. So we're good. All right, let's carry on. So that's 1 over cos x minus sine x over cos x all over cos x. Simplify that a bit. So I have 1 minus sine x over cos x over cos x. Now I haven't really done much yet, especially I haven't used any identities yet, so I don't have any quite reasons. So far I'm just doing a bit of algebra, but let's see what we can get out of this. So if I work this out, I have 1 minus sine x all over cos squared x. Oh, well, let's see what I want. I need 1 over 1 plus sine x. I feel like I have something really close. Since I have cos squared x, again, the first thing that comes to my mind is Pythagorean identity. And it tells me that I can substitute cos squared x for 1 minus sine squared x. So let's do that. So let's come up here, and let's change that to 1 minus sine x over 1 minus sine squared x. So when I see this, oh my gosh, what should I do? Well, first thing that comes to my mind is factoring. 1 minus sine squared x is a difference of squares. So let's do that. So 1 minus sine x times 1 plus sine x. Well, here we go. We can simplify that, and we're just left with 1 over 1 plus sine x, which is my left side. So therefore, left side is equal to the right side. Done. And I have proven this identity for all values of x. Okay, let's do the next, and I believe final example here. Okay, so in my last example, I see I have a pretty complicated expression on both sides. So what that suggests to me is that I'm probably going to have to manipulate both sides. And that's okay, just double the fun, right? Okay, well, let's start with the non-permissible values. If I take a look at this one, I see that if I factor this, I actually get this expression. So let's do that. So 4 sine squared x minus 1 cannot be equal to 0. So 2 sine x plus 1 times 2 sine x minus 1 cannot be equal to 0. Well, that takes care of my NPV from the right side as well. So that means that sine x cannot be equal to plus or minus 1 over 2. Well, the reference x angle that gives me this would be pi over 6. So if I take a look at it on, if I think of it on the Cartesian plane, I can have an angle here, 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 and here. So in one rotation, x cannot be equal to pi over 6, 5 pi over 6, 7 pi over 6, and 11 pi over 6. Now, how am I going to write this in general solution? Well, I could write 4, but if I take a look at these two, they're pi apart. If I take a look at these two, they're pi apart. So my final NPV is going to be x cannot be equal to pi over 6 plus or minus pi n, and 5 pi over 6 plus or minus pi n, where n is an element of whole numbers. And there's my final NPV for this expression. Right, so let's get started on this one. I'm going to start with the left side, no particular reason, but they both seem complicated. I have a feeling I'm going to have to work both sides, but that's okay. So I'm going to start with my double angle identities, minus cos x, and in the denominator, well, I already saw that I could factor, so I'm going to do that. And then 2 sine x plus 1. Okay, so again, my reason, double angle. And, well, I notice that in the numerator, both terms have a cos, so I'm going to factor that out. So cos x is factored out, and I'm left with 2 sine x minus 1. Oh, awesome. Sine x minus 1, and then 2 sine x plus 1. So I can cancel out these two, and I'm left with cos x over 2 sine x plus 1. Now this looks nothing like the other side, but I think I can make the right side look like that. So let's work on that. So on the right side, we have the expression sine squared x cos x plus cos cubed x over 2 sine x plus 1. So if I look at this again, I see that both terms in the numerator have a cos, so I'm going to factor that out. So cos x, and leaves me with sine squared x plus cos squared x, all over 2 sine x plus 1. Well, according to Pythagorean identity, sine squared x plus cos squared x is just equal to 1. So really, I have cos x times 1 over 2 sine x plus 1, which is my left side. So, which equals cos x over 2 sine x plus 1. So therefore, left side is equal to the right side. And again, I've proven this identity for all values of x except for our non-permissible values. So there you go, ladies. That's 4 examples to refer back to, and good luck on your assignment. Have a great day.